We are happy to have today Alex Oancea, who is going to talk to us about Poincare duality for Rabinowitz-Floer homology.
All right. Thank you very much. I'm very happy, honored to talk in this Zoominar, which is not yet galactic, but large enough in order to make anyone a little bit nervous, especially that it's online. So I'll do my best to take a look at the chat. If ever I miss, for any reason, a question, don't hesitate to just turn on your mics and ask it out loud. So Poincare duality for Rabinowitz-Floer homology. This is joint work with Kai Zillibach and Nancy Hingston. Hi, Nancy. I saw you were here. The plan of the talk is to first give some motivation from loop space topology. This is actually how the whole project started, from loop spaces. Then explain a theorem which has purely symplectic content, and it's a duality theorem for a Floer-type homology group called Rabinowitz-Floer homology, and then go back to loop spaces. So first part, loop space topology. Well, I'm looking at a closed connected manifold M. There's two important spaces of loops, based loops, yeah, or free loops. So base loop means that we fix a base point on the manifold, and then we look at maps from the interval 0, 1, which take the same value at the endpoints of the interval, and where at the endpoints of the interval, I stay on the base point. Free loops means that the loop is just allowed to wander around. So I thought it is useful to gain a little bit of intuition by looking at an example. Yeah, so I'm going to just give two examples of loop homology classes on the sphere Sn. There's going to be more homology classes. And I'm going to construct them in the following way. What I drew there is a sphere. I drew in red the base point. It's here. And now fix at the base point a tangent vector. So this tangent vector determines a unique great circle, endow the sphere with a round metric. And there's an equator, Sn minus 1, right, that is orthogonal to that great circle. So now whenever you fix a point on the equator, that determines a unique plane that's orthogonal to the equator and passes through this point and the base point. And that plane will determine on the sphere a based loop. So in this way, you see immediately appearing on the sphere an n-1 family of loops, right? It's these, and so on, and so forth, right? An n-1 family. And this n-1 family of base loops determines a non-trivial homology class in the based loop space. I call it X here. And now here's another non-trivial homology class. Instead of fixing the tangent vector, you perform the same construction, but allow the tangent vector to vary in the tangent space at the base point. So you add n-1 parameters extra, and you get a homology, a 2n-1 family of base loops, which defines a homology class in degree 2n-1 in base loop space. Yeah. So immediately, even on such a simple space like the sphere, you see that loop space, base loop space, has rich topology. It so happens that the homology of the base loop space is a ring with respect to the Pontryagin product. The Pontryagin product is the product induced by concatenating loops. Yeah. And for spheres, the class X that I defined previously is actually a generator, and the class Y is the square of X. It's not immediately obvious, but this is the case. So actually, in describing loop spaces and their topology, algebraic operations, like here the Pontryagin product, are very, very useful. So what we refer generally to string topology is the study of algebraic operations on loops, loop spaces or path spaces. And I gave here a little dictionary, and immediately I will take the opportunity to also remind the connection to symplectic topology. Yeah. So there's 3 columns. The first one is about names here. The second one is about algebra, and the third one is supposed to explain the geometry behind. So I already mentioned the Pontryagin product, which is a product of degree 0 on the homology of the base loop space, which is induced by this concatenation of base loops. Yeah? Now, on the symplectic side, actually, it is known that the homology of base loop space is realized as the Rabinowitz-Floer homology of the cotangent fiber in the cotangent bundle. Yeah? There's also a little sign here, eta, which refers to a local system that may be necessary in case the manifold is not spin, but I will not insist on that at all. And on the symplectic side, this product is induced by the usual half pair of pairs product in Lagrangian Floer homology. Now this object, Rabinowitz-Floer homology, is something that for the cotangent fiber, besides one critical point, which reflects the topology, contractibility of the cotangent fiber, has generators given by the geodesic loops from the base point Q to itself. So now let's go to free loops, yeah, lambda. We also have a product structure here that's called Chess-Sullivan product. And the geometry behind is going to be captured by this diagram. Namely, we will concatenate free loops whenever we can, meaning whenever 2 free loops have the same base point. So inside the product of free loops with itself, there sits a codimension n space, which is actually a codimension n Hilbert manifold in the appropriate topology, which is represented by pairs of based loops whose base points coincide. And on this space, we can concatenate. So the product topologically is roughly given by a Schrieg map, right? And then followed by concatenation. And because we have here something of codimension n, we get a product of degree minus n. On the symplectic side, we have the pair of pairs product on the so-called symplectic homology of the cotangent bundle, and the picture that comes with it is that of a pair of pairs. So there's going to be another product that will play an important role in the talk. And that's the so-called Goreski-Hingston product on the cohomology of the free loops, rel constants. There's also a based version, but I will not talk about it. So now, it's in a sense, I mean, one of the messages of the talk is going to be that Goreski-Hingston product is dual to the Chess-Sullivan product, and the picture that is dual to concatenation is splitting. So we look at families of loops, and whenever a loop in the family passes again through its own origin, we split it into 2. But we do not specify the time when it passes again through the origin. So we look here at the space of free loops across the interval. Inside there sits something that wants to be codimension n, which is the space of pairs consisting of a loop and the parameter s, so that at time s, the loop passes again through its own origin. And on this space, which I call f, I can cut. Yeah. So this I described as a kind of homological, the picture is homological, and we can see homological operations. So the cutting is something like a coproduct, right? I have some family of loops and I obtain two other families. Dually, if we reason cohomologically, this gives rise to a product on the cohomology rel to the constants. And why rel to the constants? It's because this condition that the loop passes again through its own origin is trivially satisfied and is not at all a transverse condition at 0 and at 1. So this results in a product in cohomology of degree n minus 1. And I will explain in the course of the talk that on the symplectic counterpart, which is symplectic cohomology in positive range, there is a pair of pants product, which is of secondary nature, and which is roughly described by a picture of this kind. Yeah? Like we have some coproduct type operation, but parametrized on an interval, and there's some degeneracy at the endpoints of the interval that I will make precise. So these are three instances of operations. Yeah. And in order, there's of course, I haven't pronounced one single name, and there's a lot of names who are involved in this. So generally, isomorphism between symplectic homology and homology of free loop space is known by the name of Viterbo isomorphism. There's various proofs and enhancements, including algebraic structures, that were due to Salomon Weber, Abondandolo Schwarz, Abu Zaid, Krag, Ritter, Seidel, Chelibak Lachev, and we will also have our own little contribution to the story, especially related to the cohomology product. So I started by giving some intuition about topology of based loops. I want to give some intuition about topology of free loops, again on this, in the case of the sphere, so that these operations maybe become a little bit more concrete. So again, I consider a sphere that's odd dimensional, and maybe one of the most pleasant ways to capture and understand the topology of free loops is by looking at the Morse theory of the energy functional, which is given by the integral over 0, 1 of the norm squared of the derivative of the loop. So again, I look at round metric. In that case, it so turns out that the energy functional on the space of free loops is a perfect Morse-Bott functional. And I draw in this picture on the right of the central axis the homology of free loops, which is what? Well, we've got on the one hand constant loops which account for two homology classes. That's in the case of n equals to 3. And then we see that the critical points of the energy functional are closed geodesics, i.e. great circles, and each such closed geodesic is determined uniquely by its starting point and its speed. So we have a whole bunch of unit cotangent bundles of the sphere, right, corresponding to great circles traversed once, great circles traversed twice, and so on and so forth. Yeah. So you need, in case you see, there's more information in the diagram, but if you see it for the first time, you may just retain, oh, it's complicated. If you want to put some order into the diagram, you should identify these blocks, constant loops, and then one block that carries the topology of the unit cotangent bundle of the sphere for each multiplicity of great circles. Yeah? For example, here's an example in this picture of a homology class, right? Previously, I explained that when we have a base point and a tangent vector, we get an n-1 parameter family of loops. Now, on an odd-dimensional sphere, pick a non-vanishing section of the tangent bundle, which is these thick vectors here, and that immediately allows you to spread the previous construction of X all over the sphere, right? So this gives to you a class that I call U, which is in degree n-1 plus n, because I let the base point vary over the whole sphere. And what does it mean to take Chern-Sullivan product with the class of a point, which I call A? Well, I just fix it. So A times U equals X. So that's the story, and maybe some intuition about the free loops of the sphere in homology. And then in cohomology, I chose to draw them with this weird grading, which will be explained in the course of the talk. Now, if I take free loops, rel the constants, yeah, I see blocks, yeah, again, that repeat. And I chose this grading, minus star plus 1. There's these two guys that are missing, that I drew in red, which is the topology of the constants in cohomology of the free loop space. And maybe one more piece of information, which relates now to the multiplicative structure. In homology, there's a class, theta, which is a kind of, it's very fundamental, but also it acts as a kind of fundamental class, yeah, which is the class given by the simple, which is carried by the simple great circles, right? So I take all great circles all together, and this defines a homology class here. Multiplying by that is like a kind of elevator that allows me to pass from one block to the other. So this theta allows us, by multiplication, to pass from one block to the other. And of course, multiplying by great circles that are traversed once increases the number of times that great circles are traversed. So it's not unbelievable, right, that it carries me from one block to the other. Remarkably, a similar phenomenon happens on cohomology, although it's a little bit more complicated to see, and it appears as a little bit of a miracle. Yeah? There is a class which allows us to move from one block to the other with respect to this cohomology product. So to be retained from here, blocks, both in homology and cohomology, and classes that allow us to pass from one block to the other, both in homology and cohomology. So the starting point of our story is a number of symmetries and the number of puzzles related to these products. So you have already seen this symmetry between the multiplicative structure on homology and cohomology of free loops on spheres. There is also symmetries which involve Morse theory of the energy function, or rather its square, which has the same unit, measure unit as the length. We can associate to any homology class a critical value given a Riemannian metric. To any cohomology class, we can also associate a critical value. And there's a fundamental relation between critical values of the product and the sum of critical values, and they are reversed. So we have the symmetry between homology and cohomology. How to explain them? Yeah, this one about critical values, maybe it's not so difficult, but there's many more and much more subtle that have been observed by Nancy Hingston over the years. And I want to present two puzzles, which also serve as motivation. Yeah. The first is something that already was strange, namely, there's an asymmetry in the domain of definition. Yeah. The loop product in homology is defined on the whole of the homology. The other one is defined on relative cohomology. The first one has the flavor of a primary operation. The second one has the flavor of a secondary operation because it appears from a one-parameter family. The first one is unital, the other one not. Right? Though they behave very similarly. Why? And how to explain this? And here's another piece of a puzzle, a conjecture suggested by Sullivan. So because I'm going to compose operations rather than denoting them by dots, it's useful to give them names by letters. So I'll denote mu, the homology product, and I will denote lambda, the homology coproduct corresponding to the cohomology product, right? So any product in cohomology can be phrased as a coproduct in homology, yeah, by just algebraic duality. There's nothing mysterious there. And so Sullivan suggests that when I take two inputs, right, here, I first apply the product and then the coproduct. That's the same as these pictures, namely apply coproduct on the first input and then pair the second leg with the second input and apply the product, or apply the coproduct on the second input and then pair via the product the first input with the first leg. So the main point, again, the actual content of this maybe is not so important, but what I would like that everyone remembers is that these are not TQFT type relations. Yeah? A TQFT type relation would mean that the picture on the top is equivalent to any of the pictures on the bottom, certainly not to their sum. So this is something different, yeah, of a different nature. And by the way, it's not even clear how to make sense of such relations because the domains of definition of mu, the product, and lambda, the coproduct, are not the same. One is defined on the whole homology, the other one only on the homology rel constants. And even if the constants are just teeny-weeny with respect to the whole homology of the whole free loop space, still they forbid us to write meaningful equations. So we will solve the puzzles and explain the symmetries with symplectic methods. This is what I would like to explain. And maybe it's a good point if anyone has questions. Oh, sorry, there was already a question. This picture is for n equals 3, indeed. What I drew before here, the sphere, it's specifically for n equals 3, which is the first interesting odd dimensional sphere, but the same up to just scaling would hold for any odd dimensional sphere. And as a matter of fact, with Z2 coefficients, also for even dimensional spheres. So I will now go to the second part of the talk, which is symplectic, and is about this, the title. Here I was asking, I'm confused by your TQFT remark. Are you suggesting that if the plus were a tensor, then it might look like a relation in a 3D TQFT with a 3-cobordism with boundary or 3 pictures? Yes, I believe I am suggesting that. And ultimately, one can see that this relation is obtained by realizing the various pictures as boundaries of a triangle. But I will actually present an explanation which is slightly different. So, Rabinowitz-Floer homology. This is an object that was defined by Kai Zillibach and Urs Frauenfelder in 2009. The definition that I will give will nevertheless be different from the original one, and it is phrased more in symplectic homology terms. In any case, the setup is that of a Liouville domain, which is compact symplectic manifold with boundary, so that the symplectic form is exact. I denote alpha the primitive, and what we call the Liouville vector field, i.e. the dual of the primitive with respect to the symplectic form, points outwards along the bound. So here in the picture, we have the domain. It's thought to be compact. There's a primitive. The Liouville vector field has to be thought as pointing outwards along the boundary. We can turn it into a non-compact object by adding a semi-infinite cone over the boundary. And such an object has the fantastic property that the boundary is a contact manifold with the restriction of alpha as a contact form, and as such carries a Reb vector field, which gives life to the boundary. So it is useful to pick coordinates here. I will denote R, the coordinate in 1 infinity. At R equals 1, I am on the boundary of my manifold, and the symplectic form on the semi-infinite cone is d of R alpha. And now the kind of Hamiltonians that we want to consider are as in the picture. In symplectic homology of the manifold W, one would look at Hamiltonians that are roughly 0 inside the domain W, and then which increase steeply towards the boundary. What we want to do is look at Hamiltonians which are pinned to 0 along the boundary and increase steeply on both sides. Yeah? So for such an object, the one-periodic orbits on level R are in correspondence with the closed Reb orbits of period H prime of R, and their action is RH prime minus H. So I'm writing this formula just in order for those who earn their daily bread from Floer homology to know what my conventions for the action are. And I denote Rabinowitz-Floer homology by SH star of the boundary. Sometimes we call it with Kai-Zillibach symplectic homology of the boundary. And it's obtained in the following way. There are some limits happening here. And the meaning of the limits is the following. So we look at such Hamiltonians and we look at truncated Floer homology in some action window AB. We fix AB, which are finite, and let the slope of the Hamiltonian go to plus infinity on the right, minus infinity on the left. We take a first limit. That will have the advantage of throwing out the orbits that appear in this region because they acquire very negative action. And then we first let the negative bound on the action go to minus infinity, and subsequently take the positive bound of the action go to plus infinity. So this is an inverse limit, this is a direct limit. So morally, you have here infinitely many, in a generator, you have potentially infinitely many orbits contributing in the negative range, but only finitely many in the positive range. So that's for homology. And cohomology is defined similarly. I mean, from the same Hamiltonian, except that rather than picking homology, Floer homology, we pick Floer cohomology. Yeah. Again, we will let the slope of the Hamiltonian go to plus infinity, minus infinity, and then we will take an appropriate limit. Now, the main point of the construction, and which explains the order in which we take the limits, is the fact that we wish this object to be a ring with unit. So I want to explain why symplectic homology is a ring with unit. Yeah. We have here a picture of a pair of pants, right? Here. And we have a Hamiltonian coming in. Inputs are positive punctures, outputs negative puncture. Because of usual constraints in symplectic homology, maximum principle, we need to put here Hamiltonian orbit of twice the Hamiltonian, at least, if not many more times. And the point is that pair of pants product act in truncated Floer homology as such. If I take, oops, sorry, forgot to put on my marker. If I take Floer homology truncated in some action AB and take product, I end up in Floer homology truncated in action A plus 2B, A plus B, 2B. So this is important because now, after letting the Hamiltonian go to infinity, we first let the limit A go to minus infinity. And so it will go to minus infinity both here and here and here, regardless of the value B. Whereas, and then we let B go to plus infinity. Whereas if had I taken first the limit over B going to plus infinity, I would have gotten nonsense on the right-hand side. Okay? B going to infinity means the action window is just moving away and I see nothing. So the order in which we take the limit is important and endows our object with the structure of a ring. And it does have a unit. So now, half an hour through the talk, time for the statement of the theorem, which is the main point. It's the duality theorem. And the first part says that cohomology, right, symplectic cohomology of the boundary, also carries a unital ring structure with a product of degree n-1. And there's a canonical isomorphism of unital rings between homology and cohomology. The first one is going to be related to the Chess-Sullivan ring. The second one is going to be related to Goreski-Hingston ring. And I'm going to give a first proof in a second, but I just want to stress that this is, we call it for the time being Poincaré duality, but it's not the tautological kind of Poincaré duality that we're used to. Yeah. Like flipping the Hamiltonian from H to minus H. There is genuine content to the theorem which goes beyond just a mere identification of complexes. And this is going to be apparent in the proof. So here's the proof. Yeah. It goes in 2 steps. It's about identifying a homology group with a cohomology group. So I will first, using so-called Poincare duality in Floer homology, put them on the same setting and phrase them as homology groups. So that's how Poincare duality acts. Cohomology of a Hamiltonian is the same as homology of minus the Hamiltonian, where I get a minus sign in the grading, I get a minus sign in the action. Yeah? So that means that if for our Hamiltonian H, I wanted to compute Floer cohomology, it is the same as computing Floer homology for this green Hamiltonian that I'm emphasizing here. Yeah? So now it's about, the theorem is about relating with products the homology of this Hamiltonian and the homology of this Hamiltonian. Yeah? That's what the theorem is about. And the two are related by a deformation argument. Namely, we're going to put them together by looking at a picture as follows, right? A Hamiltonian that goes like zigzag, right? Now, we will ignore whatever orbits appear in this region for action reasons. We will not care about them. So we focus on this region where the Hamiltonian zigzags. And here we see 2 kinds, right? We see a V and we see a hat, right? In other words, we see as a part of my Floer complex for the zigzag Hamiltonian, I see the Floer complex of the V Hamiltonian and the Floer complex of the hat Hamiltonian, and I want to relate these two. Well, the complex of the whole zigzag Hamiltonian actually looks as follows. There's something happening in the V part, there's something happening in the hat part, and there's maps going only from the V to the hat. Yeah? We cannot have maps going from here to there by some refined form of the maximum principle. So these, like this, are forbidden from the hat to the V. Otherwise said, this whole object is a cone. It's a cone of a map which is represented by a corresponding component of the differential going from the V to the hat. And the observation is that this whole business is acyclic because it can be deformed to the linear Hamiltonian. So I can put together the 2 complexes that interest me in such a way that the cone is acyclic. It means that they are isomorphic. As a consequence of the fact that the component, that this component of the differential is a homotopy equivalence, we get an induced product of degree now minus n+1 on the symplectic homology of this Hamiltonian, which by the tautological Poincare duality argument in step 1 is the group that we wanted to look at. So this proves an isomorphism and defines a product on the cohomology in a kind of indirect way. Yeah? I induce a product, and then, of course, the isomorphism is going to be, by definition, an isomorphism of rings. So certainly I want an explicit description of that product, and this is what I want to explain.
Alex,
Yes.
there is a question from Kyler.
Yes. Is SH of the boundary defined for a non-exact symplectic manifold with contact type boundary? In that case, the action filtration wouldn't strictly be well defined. I completely agree. In the setup that we consider, we only define it for exact manifolds. Now, that being said, if I go back for one little slide, even for non-exact manifolds, if we look at that, this part is a subcomplex because not for action reasons, but rather for geometric reasons, there cannot be differentials going from here to there. Yeah? It's my favorite argument, saying that whenever I have differentials going like that, they would need to approach their asymptote here from above, and then the maximum principle would apply. So many things can be done also in the non-exact setting. Does this, perhaps this answers a little bit the question. So now comes another important part in the talk, namely how to define intrinsically, directly, a product on symplectic cohomology. And I will define this product on the symplectic homology of this hat Hamiltonian here. Yes? Yes, absolutely. There's purely SFT formulation with augmentations. Yes, I agree, Georgios. Which we do not work out in any way, but maybe in reply to your question or remark, this Rabinowitz-Floer homology is closely related to Toulouse homology, or a version of it. So let me now explain the product on symplectic homology of this hat Hamiltonian. Yeah. I would like to look at this Hamiltonian, right? And then at this monotone homotopy, which straightens it up. Yeah. So from a Hamiltonian with slopes mu and then lambda, it deforms it to a Hamiltonian that has straight slope mu. Now, if we decide to ignore the orbits that live in this region, we see that this deformation is actually towards a Hamiltonian whose Floer complex is null. There is no orbit in this region. Okay? We want to put these in a family. And here's the family. Yeah. We put it in a one-parameter family where this is the kind of picture that would define the product. Yeah. And now we look at a degeneration of the equation where at one leg or the other, we insert this continuation map towards the blue Hamiltonian H mu mu, whose Floer complex is 0. This is the one-parameter family that we want to consider. Yeah. We count now rigid configurations in this one-parameter family, i.e. index -1 configurations, where the equation moves from continuation map followed by that to continuation map followed by that on the second leg. Of course, what we see, if I denote sigma, this operation, the boundary, the bracket of the boundary with sigma, so the defect of sigma from being chain map, is now given by multiplication followed by into which I plug C tensor 1, where C is this homotopy, respectively 1 tensor C. Yeah? So this is the equation that we get. And because now the Floer complex in a given action window of that Hamiltonian H mu mu is null, we get that the map C is absolutely 0, and so sigma is genuinely a chain map. This is the product. This is our product. The degree of sigma is minus n plus 1, minus n from the usual degree with my degree conventions for a pair of pairs product, and plus 1 because we count in a one parameter family. And then here we see that sigma is of a secondary nature because the primary pair of pairs vanishes since it factors through C, and it vanishes for two reasons. We can factor it through C at the first leg or at the second leg. This is the intrinsic description of the product, and it makes it appear as a secondary operation. Now, I wish to give yet another description of the picture. In terms of cones. So in the previous discussion, a key role was played by this continuation map C. Now, I was working with the Floer homology or Floer complex of this V Hamiltonian in this region, which is a quotient complex, and we can alternatively view it as being the cone of the inclusion of this subcomplex into the full complex. So this can be rephrased as the cone of the inclusion. But the inclusion of this subcomplex into the full one is homotopic to the continuation map from such a Hamiltonian to such a Hamiltonian. In other words, we get to the fact that Rabinowitz-Floer homology can be obtained as a limit from homologies of cones of such continuation maps. At additive level, this point of view is due to Sara Venkatesh, who actually uses it precisely in order to define Rabinowitz-Floer homology in non-exact settings. In such a setting, there is no more action filtration needed. Yeah, it's all taken into account. So the subcomplex that was bothering is actually now killed algebraically inside the cone. Yeah. So a fact that we use and which gives, that we use for various reasons, and which gives an alternative point of view of our result, on our result, is that there exists a systematic way of endowing cones of continuation maps in Floer theory with multiplicative structures, so that this isomorphism here becomes multiplicative. So this is something that I do not have time to give many details about here, and which opens up quite widely in other directions. The fact is that the other group that was of interest to us, which is the homology of the hat Hamiltonian, can also be expressed as the homology of a cone, but now it's going to be the cone of the projection from this big thing to the small one. Yeah. So for homology, we have an inclusion. For cohomology, we have a projection. And this allows me now to give a second proof of the duality theorem via cones. And the proof is actually contained in these diagrams. I'll write here the inclusion on the left. I write on the right the projection. I'll make it a bit smaller. And because we have equivalences here between the Floer complex of this full guy and the Floer complex of this a little bit wigglier Hamiltonian, because of course the homotopy type of the complex only depends on the asymptotic slope at infinity. So we have chain homotopy equivalences here, chain homotopy equivalences here. And that means that cones of this inclusion are chain homotopy equivalent to cones of the projection. But the cone of the inclusion gives rise to the symplectic homology of the boundary, and the cone of the projection gives rise to the cohomology. And what I said before is that these isomorphisms are not just additive, they are multiplicative if we take into account multiplicative structures on cones. So that's second proof of the theorem. And now I'm ready to, I don't know, maybe you have, it's also another, I'm ready to go back to loop spaces, but maybe it's a good point for people to ask questions if they have any. I'll make it large again. Oh, but I need to, yes. So how does this relate to loop spaces? Yeah, we need to explore. We have 10 more minutes, right? So we need to explore what's the meaning of these constructions and of the duality theorem in the case of cotangent bundles. Yeah. So rather than drawing my Hamiltonians as V's and hats, I will draw them slightly curved, right? So that I have a little bit more space in order to indicate where the orbits lie. So here in the middle, we have the boundary of the unit disk bundle. That's the unit cotangent bundle. Yeah. Its cohomology is obtained via the Leray-Serre spectral sequence, viewing it as a sphere bundle of over the manifold M, essentially this way. So we have two copies of homology and cohomology of the manifold, and then there's just one little connecting map, which is multiplication by the Euler class, yeah, by the Euler number, by the Euler characteristic. Yeah. So that's this part, which contributes for the constant. And on the positive slope, we have relative homology of free loops, rel to the constants. On the negative part, we have something else. And by the duality theorem, right, we know that whatever we have here is the same up to shift as what we have on the other Hamiltonian here. Yeah? So the standard, the now classical Viterbo isomorphisms tell us that on the positive slope, we have homology. On the negative slope here, we have cohomology. And the duality theorem tells us that here we have the same as here with a shift, and here we have the same as here with a shift. So that's what the situation is. And of course, we want to give Rabinowitz-Floer homology in this situation a name, and we call it extended loop homology or cohomology. So we define extended loop homology or cohomology as being Rabinowitz-Floer homology of the unit cotangent bundle. These are unital rings by our previous symplectic construction, and the duality theorem says that we have an isomorphism of unital rings that has this form. So how do the puzzles get solved? Yeah. So I recall that the puzzles meant, at least the ones that I presented, had to do with the fact that we had an asymmetry between the fact that Chess-Sullivan product was defined on the full homology, whereas Goreski-Hingston product was defined only on relative cohomology. And there was this Sullivan relation, which is not DQFT type. So we define what we call reduced loop cohomology, which is the following. We can think of extended homology as being the cone of that map, yeah, the cone of the continuation map. And actually, our continuation map from cohomology to homology factors through something that's happening only at zero level, zero energy level, and there it's only multiplication by the Euler characteristic that matters. So actually, this object is the cone of this big continuation map, but that big continuation map from cohomology to homology factors through H0 just as a simple multiplication. We define reduced homology and cohomology to be the kernel, respectively, the co-kernel. Yeah? So the kernel of epsilon is slightly smaller than the full cohomology. Yeah? It's going to be actually the full cohomology, its Euler characteristic is 0. And the co-kernel is going to be the quotient of the homology by something really small, a multiple of a point at most. So part of our results is that these are rings. The Chess-Sullivan product descends to the quotient by that multiple of the point, and it's precisely that multiple of the point, Euler characteristic. The Goreski-Hingston product extends from relative cohomology to this reduced cohomology. There's a splitting, so inside this big reduced, this big extended object, we see as sub-rings the reduced objects. And again, this means that if the Euler characteristic is 0, say if the manifold is odd dimensional, then we genuinely see the whole Chess-Sullivan ring and Goreski-Hingston ring extended inside this big object. And the Sullivan relation gets explained at the level of reduced homology as being part of associativity for the product on extended homology ring. So Sullivan relation is now actually just one aspect of associativity of this extended product, which merges together Chess-Sullivan and Goreski-Hingston product. So how are the symmetries explained? Well, actually, any statement about homology gets generalized to a statement about extended loop homology. Similarly, for cohomology, we get generalizations to cohomology, and these are equivalent under duality. For example, the one that I presented about critical values is that here we had this fundamental homological inequality. On the other side, we had the other fundamental homological inequality. But actually, when we go via our duality, right, Poincaré duality, from extended homology to extended cohomology, the critical values change sign. So if we plug in a minus sign here, of course, this gets transferred into that. But there's many more aspects to this kind of playing around with critical values. And finally, I mentioned the symmetry between, in the case of spheres, between the structure of the homology of free loops and structure of the cohomology of free loops. So I want to revisit that in the light of the following theorem of Ubele. Peter Ubele, who was a PhD student of Kai Zilibak. in the particular case of spheres, it says that this Rabinowitz-Floer homology is a free module over a field of Laurent polynomials in theta and theta inverse, where theta is that minimal period class. So what does this mean in terms of the diagram that I presented? Yeah. So now, don't forget, for odd dimensional spheres, Euler characteristic is 0, and so our full object is going to be composed of homology and full cohomology, because the missing guys from before are now there. Yeah, there's nothing else. And so wonderfully, before we had blocks for the unit cotangent bundle, and they corresponded to circles traversed once or twice or 3 times. Then we had blocks in cohomology, which now correspond to circles traversed backwards, -1 times, -2 times. And then the constants fill up one more copy of the unit cotangent bundle of the sphere. And now we have an extremely symmetric picture, periodic, right? And theta is our previous elevator that was carrying us between the blocks in homology. Actually, it carries us between all blocks all over the place. And there's also a theta inverse, which carries us backwards, right? And secretly, the theta inverse is the previous class omega, which acted as an elevator in cohomology. So there's, maybe I will stop by leaving on the screen, which is our new blackboard, this picture. Maybe if everything has to be forgotten, perhaps the message is that inside this extended homology group, right, beautifully, the ring structures on homology and the ring structure on cohomology match together like perfectly, just like they did so in this situation. I will stop here. Thanks.
Right. Thank you very much.